Ladies and gentlemen, welcome to the Geological Society of London and to this, the 10th and final Society London lecture of 2017, and thank you for braving the weather to be with us, entitled Dangerous Neighbours. My name is Sarah Day, I'm the science communicator here at the Geological Society, and it's my pleasure to introduce our speaker, Dr. Jenny Barclay. Volcanoes are fascinating but deadly, seductively beautiful, yet at the same time repellent and terrifying. Eruptions are capable of intense variations in size and impact, and volcanic crises can be protracted and debilitating for those who have to cope with them. Volcanoes pose a risk not just to life, but also to the development of sustainable livelihoods for those who live around them. Reducing these risks means integrating our geological knowledge of volcanic processes with the social, political, and cultural landscape into which they erupt. Today's speaker, Jenny Barclay, is Professor of Volcanology at the University of East Anglia and the principal investigator of a project called STREVA, Strengthening Resilience in Volcanic Areas, on whose results much of her talk will be based. Her background is geological, with a first degree from the University of Edinburgh and a doctorate from the University of Bristol, but it was the experience of working for the Montserrat Volcano Observatory during the early stages of the volcanic crisis that convinced her of the need for more integrated and interdisciplinary approaches to the analysis of volcanic risk. She is currently a member of the Scientific Advisory Committee for the Montserrat eruption. Ladies and gentlemen, please join me in welcoming Jenny Barclay.
Thank you. It's an absolute pleasure to be here this afternoon to tell you a little bit about some of the things that we have been doing in our project, which you'll hear me talk about quite a few times, is the STREVA project. And STREVA stands for Strengthening Resilience in Volcanic Areas. And it was just that. It's a kind of multidisciplinary project, which has really been trying to look at understanding and thinking about volcanic risk. When you start to think about any kind of natural hazard, of course, the first question that we always ask ourselves is, why should we bother thinking about disasters or hazards at all? And it's very obvious, and particularly we're at the end of a year where all sorts of different hazards have put disaster at the forefront of our mind. So the processes, the physical processes themselves, are a great contributor to disaster, but this is just one example of a statistic from the UN ISDR, which is the United Nations Office for Disaster Risk Reduction, which shows that in 12 years, between 2000 and 2012, it cost $1.7 trillion worth of damage, affected 2.9 billion people, and killed 1.2 million. So clearly, mitigating the hazards that happen so that when you have a hazardous event, it doesn't turn into a disaster is something that is a really big priority for us all. But in terms of the STREVA project, this is a more recent output from the UN ISDR, and it tells us really important things about where we should be focusing our energies with this. And this is thinking about the disaster burden that there is for those countries in the world that are still going through phases of development. And what this graph shows here is a statistic for life years lost. So it's a percentage of life years lost for 100,000 people in each of different income countries. And the little red country that you see here are us. We belong in here as a relatively high-income country. And you can see that the life years lost from disasters annually are far more important in developing countries. And that's a really important thing to think about when you start thinking about the impacts of natural hazards. Once you start thinking about things like volcanic eruptions through the lens of disaster risk, there's different ways you can think about them. And something that the UN ISDR are very keen on talking about is intensive versus extensive hazards. Intensive hazards are the kind of hazards that grab the headlines in the news. So things like large earthquakes, huge volcanic eruptions. This is a picture of the 1991 eruption of Pinatubo on the left there in front of you. Extensive hazards are kind of the everyday hazards that we face. And I think probably a few of you have faced a little extensive hazard to get here, so in the run-up to Christmas with all this snow and ice. So things that are everyday attritional hazards. And we tend to think, once we start thinking about disaster risk, we start thinking about those differently. Because we've been doing relatively well in the last few years at reducing lives lost in response to hazardous events. But what we're not doing as well as is reducing the economic impacts and actually ensuring that these countries that are disproportionately affected can actually bounce back and do better and continue on their track towards sustainable development after the occurrence of these. And going back to this recent data from UNISDR, this graph here with the different shades of red shows the comparative proportion of damage that is done due to extensive risks since 1990. So the darker red colour represents the damage that has been done by extensive risks, and the lighter pink is intensive hazards. And you can see that these kinds of extensive risks, which in the case of volcanoes would be things like constant ashfall, lahars, not actually deadly, but just causing a problem, have by far the bigger impact on things like road damage, water supply, infrastructure. And these are precisely the kind of things that developing countries are already struggling to work towards having intact and relatively well developed within their domain. So they're a constant kind of attritional impact. So we already start to think about hazards in a slightly different way once we're thinking about it from the perspective of disaster risk. So in response to this, the UNISDR, in much the same way as we do with climate change, produces particular frameworks to try and reduce disaster risk. And it's kind of a clarion call to the research community, such as myself, to start thinking about disasters and to start thinking about how we can use our research to actually do things better. And so they set these goals for us and priorities. And the one that we've really been addressing within the STRIVA project is actually priority 1 here, which is understanding disaster risk and truly trying to think about that interaction between the physical hazardous event itself and then the outcome for the societies who live around it. And these are the targets that they have. We're still interested in reducing mortality around disasters, but what we really want to focus on is trying to reduce the number of people affected through their livelihoods, the economic loss and infrastructure damage. So quite a strong challenge, and that's something that we've been trying to address within the STRIVA project. This is a fantastic array of volcanoes, and I thought pictures speak for 1,000 words. And one of the things that is most astonishing about volcanoes and their hazards is how varied they are. We're actually the inventors, believe it or not, of volcanoes' top trumps, which we use to raise some money for charity with our cards. And these are actually all the images that were donated to us by volcanologists around the world of volcanoes erupting around the world. And I think they really nicely illustrate the fact that volcanoes are very varied. They have a very wide range of ways in which they behave. They have eruptive behavior that lasts for different amounts of time and that has impacts over different areas. So it makes them quite challenging when you want to start thinking about how to avert the next volcanic disaster. So this cartoon I have here kind of really tries to encapsulate that. So this is my cartoon volcano with ballistics, so rocks and stones being thrown out, ash, pyroclastic flows. And the big things about volcanoes like this is they tend to erupt not just sporadically as a one-off, but an eruption often happens over a long time. So the median eruptive length for a volcano is about 7 weeks. They're not like hurricanes. They don't do something and then they disappear off again for quite a long time. And of course, once you start thinking about risk and not just the hazardous processes themselves, when you've got something happening over a long time, then you have all of these kinds of processes, social, political, cultural processes that are going on in the background. And just as the volcano itself is modifying the landscape, people's reactions to both the hazard but other everyday things that are going on will change the response there. So that's what we're trying to think about. We're trying to kind of really think about volcanic risk as not a static phenomena that you measure in a one-off, but something that actually changes through time. So before I go on to talk a little bit more about how we've done that, it's probably quite important. I'm going to keep saying this word, livelihoods, and it's very important in the context of risk, because we think that how people act to preserve their livelihoods not only has an impact on their life trajectory, but also actually governs their behaviour in a genuinely risky situation as well. So in some senses, we think that livelihoods can have an impact on whether people or not are willing to act to save their lives. So a livelihood, what we mean here, is really the means by which individuals can provide themselves with the essentials for living. So food, water, shelter, and the capacity to secure those and the other assets needed. So do you have that little bit of leeway to enable yourself to get medicines if someone in your family gets ill? So livelihoods is the way by which you secure those. Now, something else comes into play, and this is something that we're exploring at the moment when you have volcanic landscapes. I don't know if you've noticed, you're probably not all as big a volcano weenie as I am, but volcanoes are incredibly beautiful places. People feel very proud and are very attached, both socially and culturally, to the land that they live on. And there's that kind of way of looking at it, which is important, even if you're living, even if you have a subsistence farming living, but also the fact that volcanoes themselves are a resource and they can provide things as well as take them away again. So a little bit what we're trying to look at is how that's distinguished, but really what we're thinking about with livelihoods is that, and it's caught up a little bit in that way. So an example I thought might be interesting for you, because this has been all over the news in the last few weeks, of where the dynamism between what's going on at a volcano and people's livelihoods comes into play, is of course the example of the volcano Agung in Indonesia. Have you heard about this in the news? Largely it filters through here when we're thinking about flights and people's Christmas holidays, I guess, a little bit. But it's on the island of Bali. This is a hazard map around the volcano here. So it's this little edge bit of Bali here. You can see, and these are the various types of hazardous flows mapped out. And what these circles represent is the areas which people will be evacuated beyond when they raise the alert level here. And we started hearing a lot about Agung in the last few weeks, but actually it started kicking up. This graph here is from Magma Indonesia. It started kicking up in terms of earthquake activity in the middle of September. And so people started to become worried that this volcano was going to go into a phase of eruption then. And what I've done here is mapped out here at the top the level of alert and warning level here. So very quickly, because they weren't sure what was going to happen, it went from yellow to orange and then up to red. And when it's at red, broadly speaking, everyone beyond this circle here, you're not allowed into that area to live. And that means, pretty much for the whole of October, people who live and work on the slopes of Agung have not had access to that land. And they have also been living in shelter conditions for some of them, many tens of thousands of people. You're probably all about to have a very jolly holiday, evacuated to some of your relatives' houses. You think about how that's quite good fun for a couple of days, and then after a while it starts to become a little bit old. So this is really quite a challenging social situation that they're in here now. And interestingly enough, the kind of signs from the earthquakes are relatively less intense, but actually the eruptive activity started to happen here with Agung. But it provides a really nice example of how there's all of these dynamic social processes. Meanwhile, large international processes which govern the movement of tourists, the insurance of tourists, have started to kick in. So really, it's quite a dynamic situation. Things change very rapidly, and what we would be very grateful for doing is doing a little bit better at forecasting what happens next with a volcanic eruption. One of the ways we can think about this variance with volcanoes is I've plotted a graph here of the 3,300 eruptions of known duration. The percentages are showing here of each duration. And you can see here that the median duration of 67 weeks plots in the 1 to 6 month bar here. And around about today, assuming that the explosion that they had a couple of weeks ago is roughly when Agung will be deemed to have started, you can see that it's sitting in around here. So it's actually nothing special at all in terms of eruptive duration at the moment, and could probably carry on for some considerable time in terms of duration. So volcanic eruptions are actually an incredible exemplar of both intensive and extensive hazards. They're a natural laboratory for thinking about dynamic risk. So one of the questions that I asked myself while we were working on the Striva project is really thinking about volcanic risk. Can we get any insights from the people who were killed? Now, this might seem a slightly macabre way of looking at things, but basically fatalities are very well recorded. Who was sneaking about inside what evacuation zone or who narrowly escaped with their life is not the thing that people tend to report. So what I wanted to find out is, relative speaking, since 1985, so for the last 32 years or so, how many of these fatalities have actually been the result of insufficient warning or the result of people, as you often hear reported, actually doing something in response to the fact that they're trying to do something relative to their livelihood. So this is actually in total, over the last 30 years, there hasn't been a really big mass fatality event, I guess. There's just over 2,000 people represented here. But these proportions of people represent, the blue people represent the percentage of people who were killed outside of a declared evacuation zone. The red people represent those who were killed when an evacuation zone wasn't even declared. But the orange people represent the percentage of people who were killed where there was an evacuation declared and a warning in place, and they were where they shouldn't be anyway. So effectively what that tells us is a little bit about what we should be thinking about when it comes to thinking about dynamic volcanic risk. Clearly, we still have relatively incomplete understanding of volcanic impacts. And that's a little bit different to predicting or forecasting the onset of an eruption. It's actually thinking about the stuff that comes out of volcanoes, the lavas, the pyroclastic flows, and the lahars. It's actually thinking about the impacts of those and when they will interact and cause fatalities. The red people kind of do represent that inadequate volcanic forecasting. So those geophysical methodologies that we have, we need to improve those as well. But the orange people actually recognize that sometimes what we have is not an eruption where we don't understand physically what's going on enough. It's that we have a combination of poorly anticipated social processes. So something was leading people to be inside that evacuation zone, despite the fact there was perfectly adequate warnings outside. And we have to, as scientists, step away now a little bit from that thinking where what we have to do is explain it more clearly. It's actually we have to understand that there's some things that are going on in people's lives that cause them to make choices. So, for example, you were looking out the window, you thought, it's snowing. Will I come to this JOLSOC lecture or not? You leave. That's great. But imagine if your cat was sick just as you were about to step out the door. Maybe that would be enough to make you not come. Okay? And it wasn't anything to do with the publicity. It was just to do with what's going on in the background for you. So here's another graph, really, that just shows, again, not all, as happens in the disaster movies in Hollywood, not all volcanoes start with a sudden explosion. And that's shown at us written large at the moment with what's going on in Agung. So this is the difference between the start of a volcanic eruption and a paroxysm, where a paroxysm is considered a big explosive eruption. They think of it as something that is much larger than any of the explosions they've had at Agung thus far, for example. So with relatively large impact. And you can see that interval here is a day here. So these are the ones that kind of start with a bang here in blue, the paroxysm events. But you can see there's actually quite a wide distribution going all the way up to more than 20 years since the onset of the eruption, when it finally decides to go big and have one of these kind of intensive volcanic events. But you can see the majority here kind of sit in and around here. And actually, in terms of fatalities, there's quite a nice tally in. I've shown it in orange as a percentage of all the fatalities, and then in grey just as the percentage of the events that I've recorded. You can see there's a relatively similar distribution. So it's telling us that we need to do better in terms of forecasting and dealing with the fact that volcanic eruptions typically do go on for longer than we have, and we do actually have to think about forecasting and dealing with how we move between these intensive and extensive events. So, luckily enough for Striva, which started about 5.5 years ago now, this was how we defined our challenges, and they sit very nicely actually in terms of what the broad global data set is telling us about volcanic behaviour. So we had kind of 3 strands to what we wanted to do. More effective monitoring, translation of monitoring better into warnings, better prediction, improved formulations for risk, but importantly, something really new that we've been trying to do is thinking about dynamic risk. And then something where we actually want to think about how the mechanisms where we provide volcanic risk advice, how that actually can be taken up. So believe it or not, it is very hard for volcanologists to believe, but for people who live around volcanoes, whether their volcano is going to erupt or not is often not the #1 priority. And often, many volcanoes, something like 68% of volcanoes are in the tropics, and people have an annualized cycle of intense rainfall and all the hydrometeorological hazards to deal with, as opposed to a 1 in 50 or 1 in 100 chance that the volcano is going to erupt. So we have to think a little bit more creatively about where volcanoes sit in the disaster risk spectrum too. So the reason we had such a well-informed research program is largely because of our project partners. We were working in Ecuador, Colombia, and the Caribbean. And we partnered with the local monitoring organizations here. And what they brought to us, this lovely pile of books, represents the collective wisdom that they brought from dealing with all of these within their monitoring memory, largely volcanic eruptions here. And what that enabled us to do is to define, we were able to define targets together. And that's actually because the research program, which was quite unique in the research councils at that time, had a pilot phase. And what that pilot phase really did was it enabled us to have a pretty robust conversation. Obviously, what we want to do is go and fiddle with the rocks that we're really interested in, but what we want to do is make sure that the research that we're doing is actually useful. So that's where they sowed the seeds of a rebellion. We kind of were quite, it gave us energy and to kind of think about trying to do the research process a little bit differently. So this is the same again. These are what we were defined for us. So in terms of physical, one of the things that we really wanted to look at is quite often what you see are the earthquake data, but what our monitoring partners were telling us is what we need to do better at is defining different strands of data that come in during a volcanic eruption, and in particular, making use of new satellite-based methodologies. They're fantastic because that imagery can be got through large international cooperative bodies, and people don't actually have to have vast amounts of money to receive that imagery. And very strongly, our partners wanted to learn how to use that imagery better. Then coming to the Lahar impact, one of the things we wanted to focus on are these sediment-charged floods that come down from volcanoes. All of our partner countries are largely lying within the tropics. So hydrometeorological remobilization of volcanic deposits is a really big deal. And they said, frankly, the models aren't up to snuff in terms of what we want to do in terms of forecasting it. So we think you can do better with that, thinking about ash impacts. And then we had some social processes that we're interested in, which I'll talk relatively less about. So risk communication methods, and then looking at social vulnerability and governance. So this is a graph that represents some of the work that was done using satellite interferometry. And this was done by my colleagues at the University of Bristol. And they just did exactly what I was just talking about globally with the volcanoes, is they produced a global data set of where volcanoes had been observed to deform. So what the satellites are able to do, if you imagine the ground, as the magma is making its way up to the surface of the volcano, the ground starts to move. And what the satellites can do is they can measure with millimetric precision the displacement of the ground as it moves up. And as more and more satellites, there's just been a new satellite launched relatively recently, which is starting to retrieve new data, people can see more and more information about what's going on. And broadly, what they did is they went to have a look to see whether deformation is a good predictor or not of a volcano on its way to eruption. And what this data set, they actually borrowed this from medical diagnostics, believe it or not, the ideas of true and false positives and how good they are at actually forecasting. So it's thinking in the same way as the geophysical data is the same thing as a symptom of an eruption. They basically, she established the fact that what you would expect to see is that if you start to see deformation, you're moving into the zone where you could probably expect an eruption to happen with about 50% probability. And that's much improved over what we would expect before. It gives us a much greater sense that an eruption is still going to happen. Notice we're still not moving into the zone where we think we can actually forecast this. And very importantly, I think something that came from our pre-consultation through the broader umbrella of the COMET group in the UK, they have made all of that data publicly available, gone back to the volcano observatories and showed them how to retrieve that data. So people who are working on volcanoes around the world can retrieve the data using this database here and actually look at it in near real time in order to kind of interpret what's going on at the volcano. And that's a huge improvement because a very high percentage of the world's potentially active volcanoes are not actively monitored. Here's another example here with our lahars. So these flows would come down the flanks of the volcano here. And one of the things that's really interesting about lahars as a cold academic is the fact that what they're capable of doing is they actually gather material up with them as they're moving down through the slopes of the volcano, and then they're actually capable at other times of depositing that back out. And something that we're less good at doing was getting a sense of how quickly this would come down the hill given these particular processes going on. So this is a model, again, another team at Bristol have been developing recently, and what they're doing is actually looking at how you change topography, you change velocity, all of the differences change in terms of whether you're dropping particles in or out of the flow, which in turn has a huge impact on how it inundates the surrounding area. So they're at the point now where they're working on model calibration and having a look to see how well this does at actually forecasting the impacts of these flows. Because remember, a very high percentage of the people in my little analysis had actually been out with an evacuation zone, and it had actually been poorly predicted where they were. So it tells us that we should be doing slightly better at understanding these flows. And again, this photograph is just to show you that in terms of how we set the project up, was to have, and this is what we've been doing in the last year or so of the project, is to make sure that there was training with the people in the observatory, this is in Colombia, to be able to use the model. And then if you fancy a play yourself, this model is freely available as an open source tool with different topographies so that people can go in relatively rapidly and use these models in order to kind of predict where they think things are going to go. So it's been important, I guess, throughout the project that we've kind of made sure that we've had a phase where we've gone back and talked to people. Because quite often, academic research that's directly relevant to helping people with volcanic eruptions is too difficult to access on the budget and the timescale that you have to be able to put it to work. So we've kind of had to made sure that we've been able to push things through for work. But really, I've been kind of skirting around the issue. So we've done quite a lot of work with dynamic risk, effective monitoring. But really, I've been kind of skirting around the issue that one of the things that we really wanted to look at was dynamic risk. And we had to take a bit of a pause at the start of the project, really, because there was no template for how to do that. I'm sure those of you who've studied risk at school, and particularly risk in the context of natural hazards, will know risk equals hazard times vulnerability or hazard times capacity to cope. But what does that actually mean in practice? And what does that actually mean when you're trying to think about dynamic interactions between things? So what we decided to do is we decided to take part in a process that we called the forensic analysis of risk. And basically what we wanted to do is take the wisdom, which has been cleared off in these books now, come back and re-examine it through a variety of different ways and actually look at the drivers and the outcomes of past events to try and understand through an evidence-driven approach of what was the key feature. Everyone will have an opinion post hoc about an eruption, what was the real thing. You know, you think about what's going on at Agung again in the moment. Is it the fault of the insurance companies that people aren't visiting there? Is it to do with the warnings? But what we wanted to do is actually look to see how these events are actually interacting to try and understand dynamic risk a little better. So you're probably if you have a geological background at all, you're maybe more familiar with the forensic approach in the context of looking at rocks and trying to use it to pick apart the histories that are recorded in the textures that we see in rocks. Those of you who don't have a geological background, you're more familiar with it from the idea of a crime scene. So effectively, we're thinking about the volcanic eruption as a crime scene and bringing in a multi-talented team who've all got different types of specialism and actually asking them to contribute what they think the different pieces of evidence are in terms of trying to piece that together. And I know that sounds quite simple, but it's surprisingly little done. So these are our lovely forensic volcanoes, the beautiful Tungurahua volcano in Ecuador, which started erupting in 1999 and has only in the last couple of weeks had its alert level lowered back down. It hasn't had an eruption now for a couple of years, but it had a very long-lived ongoing eruption with a very sticky social introduction. Nevado del Ruiz in Colombia, which many of you will know, erupted fatally in 1985. It killed about 26,000 people with lahars in the middle of the night on November the 13th, 1985. As you can see from this more recent photograph, it continues to rumble on at the moment. Soufriere Hills volcano in Montserrat, an iconic volcano. As Sarah said in the introduction, it's where I got my introduction to volcanic crisis in 1996. That is still considered to be ongoing, that eruption, but it's not had any new lava at the surface for the last 7 years, I think, at the surface, but it's still showing signs of unrest. And then this is our volcano that tends to have intensive volcanic eruptions, very large, very destructive events, but it's also perfectly capable of having relatively gentle eruptions too, and this is Soufriere St. Vincent. So these are all volcanoes which have a fantastically rich record of the past eruptive activity that we could try to use to interrogate. Don't worry, I'm not going to tell you every last detail of every one. I'm going to pick out a few highlights to try and kind of convince you that this way of looking at volcanic risk is really fruitful in terms of pointing out the way ahead for how we kind of think about disaster risk in the future. Not just for volcanoes, but actually for many hazards that show intensive and extensive characteristics. So the best example is the first place we went, which was Montserrat, because it's the one that I was most familiar with. And this is just to give you a little example of some of the different types of evidence that we were gleaning. I think one of the most astonishing things is what we said, we're going to be open. No data, no things that have happened or have said are not data. Everything is data, if you like. And we asked people to come and talk to us any way they wanted about their experience of the eruption. And these bits here are two examples of this. This is a local teacher called Cupid who sang us a song, and he made seismologists cry, just with the intensity of how it felt to be in the face of that sort of volcanic eruption. This is another local resident who's illustrating here the irritations of having to live with the extensive hazard of lahars. We created timelines, but of course what we also had was the incredibly robust geophysical data set from the Montserrat Volcano Observatory, and then various kind of inquests and interventions and analyses, and the hundreds of scientific papers that have been written about this eruption. But we had similar events in Ecuador, St. Vincent, and then in Colombia. And then one of the things that we found that we didn't anticipate in the first is the best way to kind of really keep that analysis going and keep it was to come back again and again. If you ask people to share their information, it's only fair that you come back and share how your analysis is going. So this is just an example from Soufriere Hills. What this line represents here, this is 95, this is 2010 when we last had. The pink bars are when there's basically lava coming out of the Soufriere Hills volcano. And what we were plotting here was both the hazard outcome and the risk outcome. So we created timelines of decisions to evacuate the population. So when we changed the size of the area that was moved, and that was documented very carefully, and then the amount of run out from these deadly hazards called pyroclastic flows. Now, if they're kind of related in a really easy way, if you create a time series from both of these, what you should expect is you should see a nice correlation. And if hazard is the driver of a risk decision, you should expect to see a very careful correlation that's repeated again and again. And of course, that's not what we found. We did find correlations broadly between evacuation and what was going on. But when we looked at the qualitative analysis to try and establish what causation was, we found that when those evacuations were driven by surface activity, so pyroclastic flows, ash, explosions, there was a very nice correlation. When actually people were worried because there were signs of geophysical pressurization or changes that couldn't be at the surface, that correlation was much more problematic. And when we asked people to talk about the eruption, actually these are times then they talked about when trust fell away. So it told us some really interesting things about the subsurface activity of the volcano and how difficult it is for people to feel convinced about the eruption. This is a similar plotting, again, slightly smaller timescale here. So here's the first phase of eruption here, and 2000. And these are the social responses mapped out in a similar way. So how many people are living in shelters? How many people are immigrating to the UK and the EC? How many people are resettling in the north in sign to this? And one of the most important things that we found with that first analysis, which has been borne out in every place we've worked, is that vulnerability and the poor social outcomes are socially differentiated. And you've seen that in London this year with the Grenfell disaster as well. So people who had less to start with tend to end up with even less at the end of the disaster. And we need to pay much more attention to inequalities in the social processes that are going around. One of the other things that came up from having these workshops, however, is the fact that the richness of the information that's actually carried by the people who live through these eruptions as well. I think we weren't quite expecting the social data to be as rich and as wonderful as it is in terms of telling us things about volcanic phenomena and their impacts. And actually, what we ended up doing after we'd been to the St. Vincent workshop was we ended up trying to find a little bit of extra money, and we made a series of films which you can view online, which are basically recording the oral history. Because the last eruption on St. Vincent was in 1979, and people were beginning to worry that the social memory, all the richness of how to respond, was starting to die away, and so we kind of helped them to record that. And this is one of our collaborators, Richie Robertson from the Seismic Research Centre. The other thing they told us is we're not interested in people like me coming and explaining all about the volcanic hazards. They want to hear about them from the local people who are there time and again, who do the monitoring. And so we made a series of films as well with little vignettes, I guess, of Richie explaining something that was relevant to the different communities who were most impacted by that. Then, when we went to Colombia, we showed the films of St. Vincent, and they said, excuse me, why don't you do that for us too? And it turned out that a lot of people had not actually been able to share their story in this way, even though they had had such rich memories, and it was a very, very strong life event for most people who went through that particular process in 1985. So we decided to make a series of films there, because the way that they often felt represented was very much as victims. Lots of pictures of people plastered in mud being plucked out of broken down buildings. And they said, we don't want that. We want to hear about our toughness and our resilience. And in terms of disaster risk reduction, that's the absolute foundation, is people feeling like there's something that you can do in the face of the activity. So that's what we did. And this is an analysis that we did of the 3 films. We screened them in the villages using huge screens in the village squares. And then actually what we did is we asked people about how they felt. And one of the things that when you look at cultural studies is that these terrible things which say, don't do this, it's dangerous, it's awful, that show terrible things happening, actually make people more passive in the face of a hazard. And that's what we found. So this is a film that doesn't actually have any bodies in it. It just has people talking about the hazard. But nonetheless, the emotions that it invoked largely focused around sadness and in some cases resentment. However, the films that we coupled it with were exactly what we wanted, where people felt optimism, felt there's something that they can do, something that they can do for themselves in the face of that. So that was something that just sprung up unexpectedly from that process of talking and listening to people in order to understand about dynamic risk. And then the last example I'm going to give to you is actually relating to volcanic ash. And we didn't anticipate, I guess, when we first started the project, that we would spend quite as much time as we did talking about ash, because we thought, okay, ash, we know about this. There's been huge amounts of research done since the Icelandic eruption. We understand ash. But ash, in the social research that we did, came up time and time again. It's messy, it's destructive, it's an irritant. We hear about it here because it disrupts international air traffic. But for these volcanoes that are just behaving in that kind of extensive hazard, pumping out small eruptions, but you live within 10 or 20 kilometers of them, it can destroy your livelihoods, crops and livestock, and actually even impact long-term on human health. So we kind of felt we need to do a little bit more about understanding about volcanic ash. So just as some examples of this, this is people's memories of impacts from 1979 eruption. And something that surprised us there, 1979 is quite a long time ago. There's one or two of you in the audience who may not even remember 1979 here. But nonetheless, people had very strong memories of the impacts that they had experienced from that eruption. And believe it or not, the 79 eruption of St. Vincent was an order of magnitude smaller than the eruptions that volcano normally has. Nonetheless, people reported all of these impacts, which are all generated by ash. That was the only hazard, really, from the 79 eruptions. And we wanted to explicitly to understand, in a Caribbean context, which has constant floods, hurricanes, tropical storms, how that compared to some of the iconic hazards that they'd experienced hydrometeorologically. And it was about the same. People felt it had a really big impact. So that was St. Vincent. And then we found broadly the same thing in St. Vincent in Ecuador. So this is the extremely wonderful volcano of Tungurahua. You can just see in this DEM here that beautiful peak at the top here. And what our social scientists did they decided, rather than the usual bullets that you see when you've got us hazardy people are like further away, more dangerous, is they actually decided to divide the areas geographically by degree of exposure and residency patterns. So this is a little bit to do with how far from the volcano, but also got to do with how you escape from the volcano, which is very sensible. This is the town of Baños here, which has about 30,000 people. This is the zone closest in, and then this is the furthest out zone. And uniformly, what people reported was that ash was preventing full recovery from the initial phase of Tungurahua, which was slightly more acute than the later phases, although it kicked up again. It was one of these volcanoes that had a paroxysm quite far on into its eruption. So what people reported for us from all three of these zones is that they had a very strong difference in agricultural production. And we asked them a little bit about what they were doing, because people don't just stay static. If things are impacting you, then people have their own adaptation measures. And what we're trying to do is learn about somewhere like Tungurahua and find out whether their people are doing things that could be applied elsewhere. And broadly speaking, what people had done is changed the percentages of crops that they have here, which is what these scales represent, from predominantly potatoes to predominantly onions. And that's all to do with how these crops respond to ash. So potatoes have got kind of hairy leaves. Ash sticks to it, tends to be very acidic, poisons the plant, and causes the potato crop to fail. Onions, however, have got waxy, spiny leaves, which is very good at kind of just brushing certain types of ash fall off and causing less impact. So subsequently, across all of our areas here, Tungurahua had become a very strong onion growing area because it was relatively resistant to these sporadic scatterings of ash that they were getting. But then something else peculiar showed up in the data set. So you can see here, you'd think volcanic eruption here, boom, ash coming out. You'd expect more ash here, and then less ash here. And broadly speaking, the eagle eyes in you will have spotted that in the other one as well. You would expect then that the people in this sort of peachy dark red zone would be reporting much more disruption from ash, and the people further out would be saying, oh, it affects me once in a while. And actually, the opposite is true. We were seeing much more impact, and you can see it again in this data. Zone 3, this furthest out zone, are the ones who are claiming that they have much less agriculture than they had before the start of their eruption. So we're seeing a big impact here in terms of further out. And this is telling us two things. First thing, it's telling us that we don't quite understand what's going on with that ash interaction with the plant. We haven't done well enough at thinking about the impact. But it's also telling us that perhaps ash is not quite being distributed as we think, and our models aren't quite as good as we think. And this is, I guess, one of my most exciting examples for you of where taking that interdisciplinary approach actually caused us to go backwards and start to think about, hey, what should we be doing about our scientific modeling? It's not up to snuff, and it suggested new ways for modeling here. Just quickly here, this is similarly St. Vincents Ash. You can see very, very well recorded from 1902. These are brilliant samples from the Natural History Museum, which you can probably just about see here, have actually got timed amounts here. So somebody took a sheet on Barbados and actually gathered the ash between 1 hour, put it all into a pot, and then went for the next hour. Incredibly beautiful systematic observations of the type that I wish we would think about to do in the face of volcanic activity now. And that told us again, things weren't quite falling, and that distribution wasn't quite what we would expect. So what we did is we set out by actually going to see some meteorologists and saying, hey, have you got any models that could actually do a better job of resolving something that's going on with the physics in the ash cloud? So you can see here, this is the kind of resolvable resolvable field you would normally have. St. Vincent is just here. This is the northern coast of South America. This is actually the kind of grid boxes that we have where we started to look at it better. And this is just an output from this model. You can see here it's predicting ashfall thickness, and hopefully what you can see really nicely is you would normally expect it to thin away, but once you start to account for some more physics in the model and have it at a better resolution that's appropriate to thinking about relatively close to the volcano, what we suddenly started to do is to do a better job of picking up these kind of oddnesses in terms of ashfall distribution. So it's a really nice example of where interdisciplinarity helps you with others. So I think that's probably one of my favorite outcomes of the Striva projects. We actually had a meeting here in the JOLSOC a couple of months ago of the whole project, where we had all the scientists here. We had invited project partners from the countries where we were working. And I took the time during the meeting, I went and asked everybody their 3 best things from the Striva project, and then actually just totted them up to see what people had thought was best. And one of the things is that thinking about dynamic risk in this way needs to be embedded in everyday concerns and thinking about co-benefits. So benefits from thinking about better modelling of volcanic ash in terms of better modelling of intense rainfall, which is one of the things that we've been able to do in the small island context. One of the things that we found, and hopefully I've convinced you of today, is the importance of thinking about livelihoods once you're thinking about volcanic risk. It drives risk-related decisions, and that kind of counts across all timescales. Actually, one of the things that we found for the eruptions which happened a long time ago is some of these things still have resonance now. The ash is a really nice example of something that a lot of other people identified, which is where excellent disciplinary research. You still need to do research within disciplines that's highly specialized, but that research can be stimulated by working in an interdisciplinary environment. Sometimes interdisciplinarity is criticized, but in this instance, it's really strengthened across all of them. And then one of the things that the film shows in particular is that harnessing community knowledge and adaptation is powerful. And in more turn, once we produce that information, one of the things we found with the films and also our knowledge about the ash is that because we've started it out in that way, it has been it has been more likely to be picked up and people are showing more enthusiasm. And I'll just go back to this slide just to kind of reflect on that a little bit. This is just looking at the papers that we've published, which is one way of looking at the success of a research project. And it's just to show you these are papers which have broadly had themes around physical or social science, or where we started really thinking about interdisciplinary risk. So the project started here. We started publishing papers in 2013. But you can see, to start with, we were largely working in disciplinary lines. And doing this kind of stuff where we start to think about dynamic risk properly takes time and it takes energy. But hopefully I've convinced you today that that is energy well spent. So the last thing we're going to be doing with the project over the last wee while is thinking about critical interactions from the data that we've got, pulling out what we think the important things are to assess, monitor, and think about during the course of an eruption. This is a great joy, is some of our colleagues from Peru approached us with our research and said, we think this will be really interesting to apply there, so we're going to be doing a little bit of work in Peru in the new year. We've now got a great evidence base for our forensic sites, and we're going to start kind of making cross comparisons. And hopefully what we'll end up with is new means to really think about dynamic risk. And you can follow our progress on our website. And we have a YouTube channel. So if you're interested, if I've provoked your interest in any of these films, do look us up as Striva Project and take a look at the films. Thank you.
Thank you so much, Jenny, for that fascinating talk. We do have about 10 minutes for questions, if anyone would like to raise their hand. Before you ask your question, please wait for a microphone to appear in front of you, just so we can pick you up on the recording. So there's one just there at the back.
Thank you. That's on? Yes, very, very interesting. But I have a question about the distinction between pyroclastic flows, surges, against lahars. What if it's raining and you get a lot of rain mixed in with these? How do you distinguish those deposits from a lahar? And in your map, you showed them completely different in landscape terms, locational. Yeah. But what about time?
Yeah, so, well, time is one of the things I really hope you've all got from this lecture is that time is incredibly important. So things vary through time very strongly with volcanoes. Broadly speaking, a lahar is something that is a water-based flow that is carrying lots of particles. A pyroclastic flow is one where it's predominantly carrying material via the medium of volcanic gas. So they're hotter, and encounters with them are, for obvious reasons, much more deadly. Your question about what happens during the course of rain is completely pertinent and very interesting to think about. For example, in Pinatubo, there was a typhoon, went through very, very soon after the eruption of Pinatubo. So it's the point at which the predominant mobilizing medium, I guess, switches from gas to water. And obviously, when you're dealing with something that's happened relatively recently, that might be a continuum. So you might have wet lahars. Certainly, the Minoan eruption of Santorini, there's a lot of debate about were these true pyroclastic flows or were they kind of sloppy lahars for exactly the reasons that you say, because of the incorporation of the sea into them. So, but broadly speaking, I would say it's when you have that switch that goes between the two. That said, that's not very common. Mostly, you either have something that's a really ideal pyroclastic flow, where the gas transporting medium is the transporting medium is gas, or lahar is water. And then you're absolutely right. The technical term for mobilized flows of gas and ash and rocks that come down a hill is pyroclastic density current, because they represent a continuum of both laminar and turbulent flow, which is when we call it a flow or a surge. And some people prefer to say pyroclastic density current, but everywhere we work, people refer to them as pyroclastic flows, so that's habitually how I refer to them. But you're absolutely right to pick me up on that.
Thank you. Professor Barclay, I wonder if you could clarify or give us some more information about how you've addressed very high impact, low probability events. And I'm thinking in my mind of a couple of things. One is volcanism proximate to very high population densities, cities.
Yep.
And the other one is supervolcanoes.
Yeah, so the first one, which is volcanism very close to high population density, I think I've become much more convinced through the course of the Striva project that some of the things that we found out about dynamic risk, which are in relatively rural populations, applies broadly in cities. They have similar cultural, social processes. Obviously, they have more things going on in the urban setting, but broadly speaking, the physics of what happens is the same, and there are some similarities in terms of social and cultural connections. So you can learn things from the type of work that we're doing, but one of the things we're starting to think about is urban settings. So one of the places where we're starting to apply our Lahar models, for example, or the absolute type case is Cotopaxi, which is the flows from that go into the outskirts of Quito. And then another volcano in Ecuador called Cayambe as well, which has got some fairly large towns sitting around the edge of it. So, yep, I think that's true. Supervolcanoes, our project wasn't particularly concerned with supervolcanoes. I think there's an interesting question, and it brings in that dimension of time again. When you have a very large volcanic eruption, it's going to have a very immediate impact. There's going to be a very immediate response, which is going to be predominantly about saving lives. What we're thinking about is the kind of longer time frame around that. And I think some of the learning that we've done about that would be relevant to the year after a supervolcano for sure. But in terms of forecasting supervolcanoes, that wasn't really the emphasis of our project. But do you want me to tell you something about that?
Well, I was thinking, you said about the satellite mapping of ground movement.
Absolutely.
And of course, everyone's looking at Yosemite and thinking, oh,
well, so, no, of course. And the USGS are across that. So they have very sophisticated monitoring systems. They are not one... globally, they are extremely good at having the state-of-the-art across Yellowstone. But one of the things that's fundamentally tricky about volcanoes is they kind of do everything hidden behind the stage curtains. So if you imagine the bit of the volcano that we see is the stage and the play and the explosion, but all the kind of preparation happens with those curtains closed. And what we're doing is we've got a bunch of instruments where we're basically trying to detect what those movements are beforehand. And what we can't do at the moment is we can't reliably forecast the mass that's assembling itself, and then whether that mass is magma, gas, or other fluids such as meteoric water. So that's a really key challenge for many volcanologists at the moment. Yeah? Any last questions? Oh, this one just in the middle here.
Thank you. It was interesting you were mentioning about the agriculture and how it was affected. When ash falls, how long does it affect the land in an adverse way? And we understand, well, as a child, I got the understanding that where volcanoes are, the land is very productive.
Absolutely. So that's such a good question. And it's interesting. About 2 years into the project, I was like, so why is it every geography textbook says that the soils are really good if it kind of poisons the plants? So the reality is that volcanoes in the long term, and we're talking in the very long term, are extremely good because they replenish the soil with vital nutrients that help them grow. And one of the things that's been absolutely true that we haven't got to the bottom of yet is actually every population that we work with is absolutely insistent within a month or so of an ash fall, they have incredible growth. And actually on St. Vincent, I showed you the map of St. Vincent and Barbados off over here. St. Vincent calls its eruptions a gift to Barbados. Of course, if you ask people in Barbados, they deny all knowledge of this. But they say that the ash that came over created an immediate impact for the soils in Barbados. And that's something that I think currently we're extremely interested in, because obviously what we're focused on is the positive ways of dealing and coping with volcanic activity as well as the negative. But yes, they do enrich the soils over longer timescales. But something that we haven't quite got to the bottom of is the insistence that giant peppers, huge maize, is what people are telling us quite recently, and we don't know what the mechanism is behind that, or whether it's a folk tale. So we'll do some more digging.
Okay, we should probably draw to a close. Before I let you go and before we thank Jenny one last time for her brilliant talk, I've been asked to let you know that there's going to be a change to the way that people book for these lectures in future. So if you're a regular attendee, you'll still get your email notification, but we're going to be managing the bookings through Eventbrite, which is an external site. And there'll no longer be a ballot. You'll just need to sign up as a first-come, first-served basis. So look out for emails about that. And if you're not subscribed, you should sign up. And all that remains is to say thank you very much to Jenny for a fabulous talk.
I think I should whip a few slides out.
Oh, it's really difficult to know, isn't it? I don't know. You definitely had enough time left for questions, which is the main thing. Okay. I mean, not the main thing, but like quite often when there's too many slides, it's literally still 4:15 and people are still going through them.
Yeah.
No, I think
it was okay.
Yeah, I think it works.
Good. I felt in SAR, I was like, why the hell have I not got a diagram that shows what that is? Of the data that Juliet has.
Oh,
of like a satellite and a volcano to form it. I could just see them out there like, oh, another graph. They had their another graph.
I guess maybe.
Yeah. But
no,
it doesn't
I
matter.
don't know. I think there's enough of a mix of like pictures of volcanoes and research.